Hi everyone, today we'll be solving the problem products of array except self, and the problem statement is pretty straightforward. We're given an input array nums and our output array is going to be a result of all the products except the number at the index itself. So for example, let's say we have the input array 1, 2, 4, and 6. I'm just going to write it here so you see it. So we have 1, 2, 4, and 6 as our input array. And we need to calculate a result based off of the product, apart from the number at index itself. So we will have a length which is equal to the input array, and then our result at index 1 will be the product of 2, 4, and 6, which is 2 times 4 times 6, which is 48. And then at index 1, we have the product of all numbers except this number itself. So it's going to be 1, 4, 6, and the product of these is 24. So I'll write this as 24. The result at index 2 is going to be 1, 2, and 6. Basically these three without 4 itself, and that is going to be 12. And the last one is the product of 1, 2, and 4, which is 8. So this is what we get as our result or output array. Now there are a few ways to calculate this. If you see closely, basically we need to have the product of all numbers in the array except the number we're going through, right? And one way we can do is basically calculate the product of all numbers, which will be 48. And then as we iterate through each number in the array, which is 1, 2, 4, and 6, we just want to divide that. Let's say when we're iterating through 1, we will do 48 divided by 1, and the answer is 48 itself. When we're going through 2, we will divide 48 by 2, which is going to be 24. When we go through 4, we will divide it by 4, and then we get the result as 12. And then finally we divide 6 by 48, which is going to be 8. So that's one way of getting a result. But then what happens when we get, let's say, another element in this array as 0? In this case, when we want to get our result, we will go through another element, which is 0, and as per our algorithm, we'll go to our product, which is 48, and try to divide that by 0, which will be an error. So we did not want to encounter zeros in the solution, which is why this does not hold true when we have a 0 in our input array. Now, one way of getting around this is basically calculating our zeros. So you see, if we have our input array, let's say our input is 1, 2, 4, 6, and 0. In this case, what do you think should be the result of this input array? Let's try and calculate. The output here will be the product of all elements except 1, which will be 0 because we have 1 0 over here, right? So this will be 0. Similarly for 2, it will be 0 as well because the product of 1, 4, 6, and 0 will always be 0 because we have a 0 inside the array. So this is 0, and similarly we'll have all zeros except when we come to this 0 in the input array itself. what happens when we come here? When we see this 0, we will try to calculate the result as a product of all other elements except this 0. And that is going to be 48, which we've already calculated before. So here our results for this index will be 48. So basically, if you see both these input and output arrays, our result will have all zeros in non-zero input indexes, which is 1, 2, 4, and 6. But when we come at the 0th input index, we will have the product itself. So that's one way of doing it. Now let's see what happens when we get 2 zeros. So let's say our input now becomes 1, 2, 4, 6, 0, and 0. When we have this input, let's try and calculate our output. So for 1 will be 0, for all other non-zero elements it will be 0 because we have at least one 0. But what happens when we come across this 0 in the input array? Even when we come across this 0, we say the product of all other elements is going to be 0 as well, because we have another 0 which is contributing to the multiplication, which is going to get the result as 0 as well. So if we have more than one 0, the result for the 0th input element as well will be 0. And that holds true for all zeros, because when we come to the last 0 as well, this one, you'll see the product of all other elements will also be 0. So basically, our output array is full of zeros. And this will always meet the size of the input array. And I'll try to summarize this in one algorithm. So this is our first option, where we divide each element. Actually, we divide the product by each element. And for that, we need to handle two special cases. One is when we have 1 0 in input, and the second one is when we have more than 1 0 in input, because this is an edge case that will change our output array. And basically how this will pan out is we'll have, let's say, an array 1, 2, 4, 6. Now without the zeros, we want to iterate through all the elements and then divide the product by each element. So first we'll iterate through all of these, we'll calculate the product, which is 48, and then we'll divide each element. We'll divide the product by each element as we iterate through. So that is 48, 24, 12, and 8. Now when we add a 0, we want to keep a count. So we will count 0 when we're going through the first loop. And when we come across this 0, we will increase that to 1. What happens when we're calculating the product? Basically, if we come across a 0, we don't want it to contribute to the product, because if you remember, in this case, even when there is 1 0, the result for that index where we have the 0th element is still going to be the product itself, because that 0 will not contribute to the multiplication of all other elements, which is 1, 4, and 6. So we still want to keep a track of that product when we have the first 0 in our input array. So what we'll do is we'll increase our 0 count from 0 to 1, but we will still continue to keep track of our product. And then when we see that the zero count increases to 2 when we added another zero in our input, at this point we can just return an array which is the same size of our input array but is full of zeros, because even when we come across either of these elements, the zero elements, the product will still be zero because the other zeros contribute to the product. And so it's going to be 2, 3, 6. It's going to be an array of size 6 with 0 elements. So that is our first approach, and this is how it looks like in the code. So this is how it looks like in the code. When you see we have a 0 count, which we initiate as the integer 0, and then for each number in the array nums, we are calculating the product as long as that number is non-zero. If we have a 0 number, we just increment the 0 count. And by doing this, we get the product, we calculate the product of all the non-zero integers. And then we just initiate the result array, and we check if we have multiple zeros. We just want to return an array which is full of zeros, as we saw in this case. And once we check that we don't have more than 1 zeros, we go in our loop and check. The remaining case is if we have 1 0 or all elements are non-zero. So if we have 1 0, we want to make sure that we append a 0 to the result where the number at that index is non-zero, because then the 0 will contribute to the product. So we're checking if we have a 0 count and we come across a number which is non-zero, the result will always be 0. And that's the first part of the for loop. In the second one, we see that if it is the 0 element in the input array, then we want to append the product of all the other elements. And that is the second part, which is the else condition itself. And apart from that, if we don't have a 0 count, we just basically want to go through each of the numbers and divide the product by that number for that given index. And that sums up our first approach. This will be, our time complexity here will be big O of n, because we're iterating through the nums array only once in all of our calculations. So technically we're doing it twice, so it should be big O of 2n. That will be big O of n, because we remove all constants from a big O notation. And this is our time complexity. And our space complexity is big O of 1, because we're not using any other data structures to store our intermediate results. And that's our first approach. Now let's move on to the next approach. Now the second approach is basically to calculate all the numbers before and after to exclude the number itself. And we'll call this prefix and suffix. Let's see, our input array is 1, 2, 4, 6. Now, how do we calculate the product of all numbers excluding the number itself? If you're at 1, we need to calculate the product of all numbers after it. because there's no numbers before it. If you're at 2, we'll have to calculate the numbers before it and after it, and then include them in the product to get the result at this index. Similarly, for 4 and 6, for 4, we'll have to calculate the product of 1 and 2, and then basically calculate the numbers which are after 4, and then include them in the suffix product. And that is how we're going to get the result at 4, and similarly at 6. And one way to do that is to keep track of the product of all the numbers before a given index, and we do that by storing that product in the prefix array. So we're going to have a prefix array, let's say of the same size, and we initiate it to 1, 1, 1, and 1. And how we do that basically is by starting from the first index. And the reason for doing that is because for the 0th index, which is the first element in the input array, we don't have any numbers before it. So for calculating the prefix, we'll have to start at index 1, which is the second element in the array. So what we're going to do for the second element, which is at index 1, we need to have the first element as a product, because there's no elements before that. So our first element, which is I minus 1, let's say our I is at 1 here. We are at 1 here, and then we want to calculate the product of numbers before index 1, which is just 1, so this remains the same. When we move to index 2, we want to calculate the product of all numbers before index 2, so we do that by multiplying the previous result with the element at index 1. So this will be 2, and this will be the product of all the prefixes at index 2, and that value is 2. At index 3, we want to keep track of the product of all numbers before 3, so we take the product of all values till index 2 and then multiply with the number at index 2. So that is going to be 8. And this is a prefix array, which basically keeps track of the product of all the prefixes till that index. So for example, at index 3, the value in the prefix array corresponds to the product of all elements till prefix 2, which also includes 2. That is basically the value of the product of all numbers till 3, but excluding 3. So, well, that's a prefix array. Now for the suffix array, we'll do something similar, but we'll start backwards. So we have 1, 2, 4, and 6 at indexes 0, 1, 2, and 3. And now we want to calculate the suffix array. We'll start with 1, and then we want to start backwards because we want to calculate the suffix for each number, which is basically all the numbers after that given number. So for the last element at index 3, we don't have any numbers after it. So the suffix of the last element will be 1 itself because there are no numbers after it. And the reason why we choose 1 instead of zeros is because to calculate the prefix and suffixes, we are multiplying the product of all the elements up to that index with the input element at that index. So if we had a 0 instead, we would multiply 6 with 0 to calculate the suffix at index 2, and we would get a 0. So when we're using multiplication, it's important to use 1 and not 0. Now for the suffix at index 2 means the product of all numbers till index 2, which is going to be the last value itself, because there's only one number. So we multiply 6 with 1, and that's the value at index 2. I'm just going to write it better. So here we have 6. Now at index 1, this is the value of the products. At index 1, this is the value of all the suffixes till index 2 already. We are storing that in the suffix array. So the product of all numbers till index 1 would be the suffix at index 2 multiplied by the input value at index 2. This is going to be 24. And similarly for index 0, we will multiply 24 into 2, which is going to be 48. And the intuition behind it is we're storing the product of all numbers after a given number at an index. So for example, at index 3, the value corresponding to the suffix is the product of all numbers after 6, which is, well, there are no numbers after 6, so it's going to be 1. For the number 4, the product of all numbers after 4 is 6. And so on for number 2, the product of all numbers after 2 is 4 and 6, which is 24. And that's our suffix array. And so on. And now we have our prefix arrays and the suffix arrays. So at each index, if you see at index 0, the product of all numbers till index 0 before it is 1, and the product of all numbers after index 0 is 48. So all we want to do is multiply the product of numbers before a given element and after the element. So our result array will be multiplying the prefix and the suffix at any given index. So for the 0th index, it is going to be 48. For the first index, it is going to be 24. The second index, it's going to be 6 into 2, which is 12. And for the last index, it's going to be 1 into 8, which is 8. And this is our result array. Alright, let's see this in code. For our second way of solving this problem, we are calculating the prefix and suffix of the numbers at each index. And we do that by first initiating the prefix and suffix arrays. And it's important to have ones instead of zeros because we're calculating the product. And we build those prefix and suffix arrays by going through the nums array. And this is how we get the values for a prefix array, which is basically we start at index 1 because at index 0 there are no prefixes. So we start from 1 to basically the last element. In Python, we exclude the last element in the for loop. So this will be from 1 to, let's say, for input arrays 1, 2, 4, 6, 0. Our input array will be length 5. And this will go from 1 to 5, but we exclude 5. So it's going from 1 to 4 in the for loop. And we're calculating the prefix at each index by multiplying the prefix till the previous index by the number at the previous index itself. And that is going to give us the value of the prefix till index I. And to write this again, so this is how we build the prefix array. For suffix, we do something similar, but we start from the second last index. And that is because for the last index, we don't have any suffix, and that's going to be 1 itself. So we don't want to start with the last element, because otherwise it would be out of bounds as well. And we want to get the length minus 2, because the length is based on 1 index. We want to get length minus 2 because we want the second last index. And in Python, you basically just give the start value, end value, and then this is the increment or decrement of the number, and we're going from the second last index to 0 because this is excluded, and we decrement each number by 1. So we're going from, this is lit5, so we're going from 3 to 0 indices, and this is how we calculate the suffix. Is basically at any given index, the product of all numbers after it will be the suffix value that we're storing till the index right after it, multiplying it by the value in the input array corresponding to that value. And that is how we'll build our suffix array. And then to get a result, we want to multiply the values in the prefix and suffix arrays, because that just means you're multiplying all values, the product of all values before the number and the product of all values after the number, which is going to give us a result. And this will give us our output array, and we just return that. The time complexity of this will be big of n, because we're just going through the numbers once in each of these loops, and that will get us to big of n because we drop the constants. And then for space complexity, we have big O of n as well, because we are storing our intermediate values in our prefix and suffix. Now, we do that because it's easy to visualize what is the prefix and suffix values at a given index. But actually, we can reduce this by calculating this in place in one array itself, which would be the result array. And how we do that is basically by getting the prefix array. And then let's say the values are x, y, z, w. And then for the suffix values, we want to add on top of these values and not have to create a new array. And this is to save a space so that we don't use this extra space of big O of n to store these intermediate values, and instead we can just use this prefix array as our result array and then return this. And while calculating the space complexity, we usually don't include the space required for the return value. So it's going to be, once we do the calculations of prefix and suffix values in place, the space complexity will be big O of n. And this is the second way of doing it in place, and which is the most optimal solution, which gives us, because the time complexity is big O of n and space is big O of 1, because we're doing the prefix and suffix computations in the result array itself. So this is where you see the result array, and we add the product of the numbers before a given number, which is a prefix, and after a given number, which is a suffix, in the same result array. And I'm going to walk you through it real quick. So we have our result array. We need to initiate that as the same size as our input array, but with ones because of multiplication. So let's say we have 1, 2, 4, 6. This will be our result array. We initialize our prefix and suffix as 1 because we have our end cases, edge cases, which is first and the last elements. And then for each for each array in the result array, we'll first calculate the prefixes. And we do that as we did in the previous one. We start with index 1 and go to the last element. And for that, we're going to calculate, this is the input array. We're going to calculate the prefix at index 0 with input array at index 0. So this is going to be 1. For this index, we'll have, this is the prefix, or actually let's name this as result itself. 1 will have 1 into 2, which is 2, and at the last index we'll have 2 into 4, which is 8. So our result array after prefix was 1, 1, 2, and 8. And this is its index 0, index 1, 2, and 3. Okay, so now for suffix, what we're going to do is have, we will store the suffix value in the variable, right? So we'll start with the second last index, which is at index 2, and then we want to calculate the suffix value at index 2. And remember, this is our input array, and we have initialized our suffix as 1. So our suffix at the second last index would be the input at the last index into the suffix, which is 6 into 1. The suffix will be 6. But remember, in the result array, we already have the prefix value, which is 2. So now then, once we have our suffix value, we will multiply that with 2. And our result array will be updated to 12, because 6 times 2 is 12. And this will be our suffix value till index 2. So our value is 12, but the suffix value at index is 2. Now, once we want to calculate the suffix at index 1, we will multiply the pre-calculated suffix till 2 and then multiply the input value at index 2, which is 4. So 6 times 4 is 24. So our suffix will now be updated to 24. So this will be 24. And we are multiplying the suffix with the prefix value itself, which is 1. So this will be updated to 24. Now again, at index 0, we're calculating the suffix by 24 times the value at index 1 from the input array, not the result array. Remember that. So 24 times 2 is 48. And we will update our suffix as 48. Now our suffix is 48, the prefix value is 1. So result array will be updated to 48. And this is our final result array that will return, which is 48, 24, 12, and 8. And that is a value we'll return as output. This will be our time complexity of big O of n. But the space complexity is big of 1 because we're just storing the suffix and prefix values in variables instead of arrays. And that's it. Thank you for watching. Happy coding. If you enjoyed this, please consider liking and subscribing to the channel and the video. Thank you.